Hello everyone, I am Haptam. Today I will present the Uncertainty and Risk Analysis final project. The title of the project is Monte Carlo-based Uncertainty Propagation in Wflow and Muesli Sediment Yield Simulation using DAM perturbation. The presentation contains background and objective, methodology, a result and discussion, as well as the conclusion. When I come to the background section, hydrology and sediment simulation results are affected by uncertainty in the terrain DAM. DAM uncertainty can propagate through hydrological and sediment simulations. Monte Carlo simulations provide a framework for uncertainty propagation analysis. The objective is to assess how DAM uncertainty affects hydrologic and sediment simulations under different rainfall conditions. The project contains Gaussian random noise, or the project incorporates Gaussian random noise errors with 10 centimeter standard deviation, which is added to the digital elevation model. 100 perturbed DAM realizations was generated, slope, flow direction, or LDD, and static maps were updated for each realization. Wflow simulation or simulated runoff volume and peak discharge, and Muesli used to estimate sediment yield. Statistical analysis performed on 100 Monte Carlo realizations. So this is the DAM of the project, or this is the Protoponas River Basin. And when I come to the conceptual framework of the project, it has so many parameters, or the conceptual framework include the overall methodology of the project. So the objective, as I have stated before, it is about evaluating how DAM uncertainty affects hydrologic and sediment response. And the motivation is DAM uncertainty can propagate through models influencing runoff and sediment yield simulation. And when I come to the input data, Protoponas River Basin is the selected basin for the project, and its area is about 436 hectares, and the area is almost mountainous area with, or the DAM resolution is about 5 meters. So using this DAM, the original DAM was perturbed using 10 centimeter standard deviation error, and the perturbed DAM was outputted here. So using this perturbed DAM, the slope was generated, or 100 slope was generated for each 100 perturbed DAMs. We have 100 slope simulations, and here also 100, or the flow direction or the LDD generation was 100 for each perturbed DAM again. So using this, the static map was updated for the DAM slope, the flow direction, river network, and stream order. And finally, the Wflow was simulated, or the Wflow was run, and I simulated the runoff and peak discharge for each 100 realizations here. And the Muesli, or the modified universal Soilers equation, was used for calculating the sediment yield using these parameters, the existing parameters in the previous research. So for each realization, I calculated 100 results here. And finally, the statistical analysis was performed using the mean, standard deviation, minimum and maximum values, uncertainty range, like the 95% confidence interval, and uncertainty in percent. So this is all about the framework. And these are the 100 field DAMs generated by the Monte Carlo simulations, and these are also the 100 slope maps generated by the Monte Carlo simulation. And these are the 100 flow direction or LDD maps generated during the Monte Carlo simulation. And also these are the 100 static maps generated by the Monte Carlo. When I come to the results and discussion, I used two rainfall events, which are the maximum and minimum events. So the maximum rainfall event contains the 855.1 millimeter, and the minimum rainfall event contains 51.25 millimeter. And when I come to the statistical analysis of the simulation results, these are the parameters or the variables: the peak discharge, runoff volume, and the muesli sediment yield results. So here are the mean values, and these are the standard deviations. So when we talk about the muesli sediment yield, its standard deviation is very high during this rainfall event, and during this rainfall event or event 20, the standard deviation is 72.619, which is much less than the standard deviation of the event 12. And all the uncertainty is below 0.05, so the uncertainty is very low, and the minimum and maximum values are here, and this is the original value, so which is almost same with the mean value of the simulated muesli value. So that from this table we can understand that event 12 exhibits larger standard deviation than event 20, indicating greater variability under extreme rainfall conditions. Uncertainty remained below 0.05% for all simulated variables. Event 12 produced substantially larger runoff and sediment yield than event 20. The 100 Monte Carlo realizations produced high constant results. And these are the graphical or the histogram interpretation of the result. So here are the value of these two are the value of the 95% confidence interval, and here the value or the simulation or the Monte Carlo simulation follow almost normal distribution, near to normal distribution. So these two graphs indicate the histogram of the two values or the two events, event 12, the maximum event, and event 20, the minimum event. And when I come to the skewness and kurtosis analysis, the skewness and kurtosis value looks like this. So this is based on the experts Hatem here in 2022. So these are the detailed intervals or the skewness interval and kurtosis interval and their interpretation. And when I come to the discussion and interpretation, the distribution characteristics, both events exhibit approximately normal muesli distribution. Event 12 skewness, which is 0.19, and the kurtosis is 0.01. So this indicates near normal distribution. And for event 20, the distribution is slightly more peaked. And when I come to the conclusion, dam uncertainty, which is 10 centimeter in standard deviation, produced negligible effects on W flow muesli outputs with the uncertainty, which is less than 0.05%, while the rainfall magnitude remained the dominant control on sediment yield. This is enough for the presentation of the project. Thank you so much.